I will discuss two little examples where we can actually exploit symmetries of systems to obtain a closed analytic solution for size-scalable systems. One example will be the multi-mode decay model in a stationary regime, so it's not the original one which you might know from quantum optical setups. And another one will be a transport through the quantum Ising chain, which is a paradigmatic model for a quantum phase transition. Okay, so this is meant to be sort of interactive. If there are questions, just don't hesitate to ask. To motivate, well, why is it so difficult to simulate large quantum systems? You all remember, so an isolated qubit can be written, oh, sorry, I have to get used to that, can be written as a superposition of two states. So after all, you just need basically two numbers to parameterize that well. And if you now scale up the system size, well, you run into trouble already for closed systems, right? This is because basically the mathematical structure of this Hilbert space is now given by a tensor product of separate Hilbert spaces. And that simply means that to describe or to write down an arbitrary vector, even to construct the basis, you have to form the tensor product of all different basis vectors. That means that the dimension of the composite Hilbert space becomes a product of separate Hilbert space dimensions. So in case of qubits, you get an exponential scaling. That means that Hilbert space is really, really big in flat words, and for realistic quantum systems in numerical simulation or even some analytic approaches, typically unfeasible. The exception may be if only a part of that Hilbert space is accessible, so in case of symmetries present in the system. And I will just discuss particular examples of that. Now, even worse, especially you guys know all, so typical quantum systems, especially that in biological ones, in biological framework, are embedded in an environment that induces decoherence. And the typical approach to treat this is to separate the Hamiltonian into different parts. So one acting on the system, one acting on the bath, here denoted red, green and blue, and an interaction which you can now choose to treat in different regimes. And here I just discussed the weak coupling limit. For that particular choice, it's always possible to write it in a tensor product form of operators acting only on the system and only on the reservoir. Actually, note this is also possible for fermions, even though they anti-commute, but you can perform suitable transformations to map it into such kind of a representation. Okay, so in the weak coupling limit, the standard quantum optics way to obtain a reduced description of the system only is to perform the Born-Markov and Secular approximations we've heard several times. And they have the advantage of yielding a Lindblad type master equation. What does it mean? Well, it has this general structure here. So you have a commutator term of the original system Hamiltonian plus some Hermitian correction. They account for some unitary evolution, and you have a dissipative part. So here you might not now expect that an initial pure state, for example, may evolve into a mixture. And if you write this Lindblad type master equation, well, the point that it's Lindblad type is the distinctive property is that this matrix here, gamma A, B, C, D, has to be positive definite. And that property grants you that not only trace and hermiticity of the density matrix are preserved, but also its positivity. So this is nice from a mathematical point of view, but so for example, you might apply that master equation also outside its range of validity, and you might not even notice. So keep in mind, one should a bit be careful about advertising positivity preservation as the must-have. Okay, so these Lindblad operators can be written in this energy eigenbasis defined by the system Hamiltonian. And for the lamp shift Hamiltonian here, you can show within the limits of this approximation that it commutes with the system Hamiltonian. So especially if you look at the energy eigenbasis, it's quite convenient that you see when you look at populations, the contributions here will cancel. Moreover, you can see that these dampening coefficients here are directly related with the interaction. So there's basically, it's like a plug-and-play formula. What you have to do is to calculate matrix elements of these coupling operators of the system part, calculate some Bath correlation functions of the Bath part, do a Fourier transform, stuff the transition frequencies of the system in there, and you get the dampening coefficient. So it's a quite fast route. So you don't really need to do to do the microscopic derivation for each system separately, if you keep the validity of the approximations in mind, right? And there's an additional factor which is quite peculiar for the secular approximation. Here you get this Kronecker delta function. So only those transitions here are coupled that fulfill a certain energy condition, some energy conservation. And this is necessary for the preservation of positivity. What else can be said? Well, I mean, still, this couples, in general, coherences and populations. Only for the case of having non-degenerate systems, you can say that this delta in the energies becomes a delta function in states. And then the master equation further collapses into a single rate equation form. Now, although it has rate equation form, it does not necessarily mean that this is a perfectly classical picture. These energy eigenstates, in which basis that rate equation is written, they can be, for example, highly entangled. They can have strange quantum properties, but nevertheless you have this simple, nice mathematical picture. So if you would transform back to some localized basis, for example, then you would still obtain some master equation where coherences and populations are strongly coupled. So just when you say that, be careful that to specify the basis where you're in, right? Okay, you can conclude from that. So if you have, if you solve for that stationary state, you will typically end up with a statistical mixture. However, in addition to that, in the special case of a thermal bath, in thermal equilibrium, there exist some analytic properties based coming from microreversibility of these bath correlation functions. They run under the name KMS condition or Kubo-Martin-Schwinger conditions and state basically that analytic property, and there is a correspondent thing for the time-dependent form. So this is the Fourier transform of the bath correlation function. Beta is the inverse temperature of the bath, and mu the chemical potential, which we will neglect here in the following because we only have bosonic baths. And if you stuff that into that master equation, solve the evolution, you can use that condition to show that if you only have a single bath at a certain fixed temperature, it will equilibrate. So, well, in case of ergodic evolution, that means it's one stationary state. You may have further solutions. Now, the picture changes if you have multiple environments, and this is the situation which we are all interested in. And these can be characterized by either different temperatures or different chemical potentials. And that will in general induce some heat flux, or in chemical potentials you will have also matter flux through the system. And now we are interested in Berlin mainly in the statistics of this flux. So mainly matter flux, but now we also came into this heat flux business. And actually, when you work at finite bias, so in the talk by Schmul-Görwitz, we always had strong coupling between system and reservoir, but infinite bias, and now here it's the opposite regime, so we consider weak coupling, but finite bias. Then you can actually have the situation that, say, an electron hops against the bias with a finite small probability. And these probabilities, however, even in this kind of approach, they obey a relation called fluctuation theorem. You can phrase it more generally. They even obey a fluctuation theorem for entropy production, and this holds even in non-equilibrium setups, so where you have lots of different temperatures, different chemical potentials. And this is nothing but a manifestation of the second law. So if you do the math correctly, you can identify contributions to entropy flow and entropy production. And in the stationary state, the entropy produced in that system is flowing through all the terminals to the reservoirs. So you have a balance, and if you do counting statistics, as we did, for example, in the case of electrons, you can monitor these flows and reconstruct heat and matter flows, and they are the heat flows. So what you get in general for these fluctuation theorems is that the probability of observing a trajectory with a positive entropy production is much, much larger, namely exponentially larger than the opposite one. So it's like a generalization. It doesn't say that these entropy reducing trajectories are forbidden, they're just exponentially suppressed. Okay. Yes. So you get that when you take this, So you get that if you take this p minus delta s to the other side and then average over all trajectories delta s, then you get this integral form, which is also known as Crookes equality.
But you can derive it.
Yes. Mm-hmm. And actually, this is more general. It even holds for time-dependent driven system also, right? Okay, so how would we monitor the entropy flux, or in the simplest case, say particle fluxes? And we've already had an example today in the morning how you would do that microscopically. In the weak coupling limit, it's even a bit simpler. So you can attach some bookkeeping operators, say in your interaction Hamiltonian, and use a virtual detector, for example, and treat this in the derivation of these master equations as part of the system to obtain these kinds of n-resolved master equations. Now, this is not necessarily a rate equation, so these are now super operators, right? I arrange these density matrices in a vector, and that becomes a large matrix. But they have this, in this weak coupling assumption, they have typically this general form that you only couple density matrices conditioned on n particles having left the system into a certain monitored reservoir with plus minus 1 particles. So it's a kind of sequential tunneling in electronic transport. So L plus, for example, is a super operator that accounts for jumps of electrons from the system into the reservoir, and L minus describes the opposite process. Here, because we are at finite bias, right? If you're interested now in the probability, if you don't care about the system state, just in the probability of having n particles left the system, then you simply trace out the solution of this equation. I mean, it's a bit, well, this is an infinitely large set, but formally you would simply trace that out, and that gives you the probability. And well, when you look at it a bit closer at this kind of equation, you see it's translationally invariant in n, so you can simply Fourier transform that. Yes?
It appears also in principle, for small bias, of diagonal terms in n and prime.
In principle.
Why it's not there?
Yes, so this arises due to the secular approximation, basically. In principle, you can have these terms that you get coherences of the detector. Yes, that's in principle possible, but basically, when you follow this secular approximation, including this bookkeeping detector, then it only collapses to such kind of a simple form. Okay, so if you simply Fourier transform that equation, you get like a normal master equation, but which is now equipped with this counting field chi. Well, what's the use of that? Well, first of all, you have reduced dimension at the expense of introducing that parameter. And that equation you can now solve because it's finite size, right, in principle. So if you would now try to calculate this probability, you would have to perform the inverse Fourier transform, and you see that's a bit hard to do, right, because you have to exponentiate a matrix and then do some integrals. So typically, that's unfeasible. For the single electron transistor and the infinite bias limit, actually, you can do that. But in general, this is not so useful. So what's more useful then is to think in terms of cumulant generating functions or moment generating functions. And these can be defined as such. They are defined as a Fourier transform of the probability distribution. So if you are able to calculate these things, then, or even approximately, then you can simply take suitable derivatives with respect to the counting field, and that gives you all the moments. So for example, the mean you would be interested in, or the time derivative of the mean of the number of tunnel particles would give you the current. Or also the variance, right? I mean, if you consider transport in these LHCs, it would be interesting how reliable is that transport, or is there great variance for a fast transport or the probability for a slow transport? That could be learned from this variance measure here. And in particular, you get an extremely simple formula for the current. So what you have to do there is simply to solve for the stationary state of the master equation at vanishing counting field and evaluate that expression. So the only challenge is then to find the stationary state of your master equation. Moreover, if you want to do only long-term statistics, it is possible to approximate this cumulant generating function by the eigenvalues of the Liouvillean. Now, I won't discuss this route here because I want to talk about size scalable systems, and calculating eigenvalues of very large matrices analytically is typically hard. So I don't follow this route here, but rather construct the moments from the Laplace transform of that expression. So you actually don't have to exponentiate that matrix. That's what I want to say, basically. There are tricks that give you long-term limits without doing these transformations here. Okay, if this is some technical short primer, if there are no further questions, I would like to discuss a little physical model. First of all, I mean, these are extremely primitive models with a high degree of symmetry and the advantage that you can scale them up in size. And I will try to ask the question, I mean, what happens, how much quantum stuff is still in there in the large scale limit? Okay, one model is very well known, actually, if you only consider one path. So it's called the decay model, and it consists of a number of two-level atoms, so say two-level systems, and they are trapped in a cavity. And the main assumption is now that the size of this atomic cloud is much smaller than the wavelength of the cavity mode, basically, such that all the atoms sense the same field. So you have some extreme permutational symmetry here. And this is, of course, well, in a sense, unrealistic. You will always have some e to the ikr factor in principle, but this is in the limit where this k is so small that you can neglect this completely. Okay, it's an idealized model, and a further generalization is here that first you have a continuum path, so every cavity, if it's not completely perfect, has some continuum of modes, or you can also think of putting this in free space, right? Okay, and the a third generalization is actually now that we consider two paths. Why? Well, first I should tell you maybe about what's interesting about that model. Well, because you have this nice description of large spin operators here. They have a closed algebra, and you can exploit this to derive the equations of motion, say for the energy of the system, and that has been done a long time ago, so in the 50s. And what you see if you look at the energy current, so initially you would place, for example, all the atoms in their excited state and couple them to a vacuum bath. And then you would look how does the energy of the system evolve and conclude that the energy which is not left in the system has been irradiated. And well, for a single two-level atom, what you see is just simple exponential decay. For n two-level atoms that decay incoherently, well, you just scale up the result. It's just n times exponential decay. However, in this collective system, what you see is this sharp peak. And you can now solve that either with approximations or exactly, it doesn't really matter. So what you see is that the height of the peak scales quadratically in the number of atoms. The area under all the curves is the same. Of course, it's only the number of total excitations that tunnel out of the system. However, here, the size of the peak goes up quadratically, and of course, to make the area the same, the width has to become very sharp. That means hard to measure. And also, you see here, actually, in this little example, the maximum is moving to the left, so it's a very short time effect. And there you might vary, and you should vary probably about the validity of Markovian approximations or Markovian descriptions. So the main question is, can one transfer this to a stationary regime? And that's why I would like to use as a motivation why we couple this to two baths. So we think of one high temperature bath and one low temperature bath, and just are interested in this thermal flux.
So
yeah.
Sorry, you couple to two electron baths?
No, these are bosonic operators here. These are bosonic ones. So
okay.
that's just the electric dipole.
Like electromagnetic field or phonons or whatever you can think of.
Well, you could, actually they do not really have to be thermal. In principle, you can think of a cavity which you pump through a laser. You put this cloud of atoms in there and then let them radiate into some direction, and you have a detector which serves as a vacuum bath. Yeah. So that would be a different realization of that. But I mean, in this context, it's rather interesting, I think, to look at this oversimplified model as a toy model for what happens when you have strong coherences.
So what is a possible physical realization you said of this model?
Yes. Well,
what could it be?
This could be under the neglect of recoil, and so you have a bunch of two-level atoms.
Okay.
And the size of the atomic cloud here, so this diameter.
Like cold atoms, for instance.
Yes. Well, you can think of Bose-Einstein condensates also.
Okay.
They have this intrinsic permutational symmetry already. And if that size is much, much smaller than the wavelength they are interacting with, then this approximation is approximately valid, yeah?
Maybe for the equation for education, since particle effects operators, if you compare with laser, in laser we have also excited state in the first population, but they decay a bit different way, but it means induced radiation, but anyways it's decay very fast in the body.
Yes.
Is it compared with decay effect? Is similar or decay is faster on the other or not?
There have actually been proposals to build a laser based on this.
Really?
Yes, yes. But not, well, there was an incoherent pumping term and a coherent relaxation term. So it was a bit different that one of these paths was collectively coupled and the other one was incoherently coupled, so with a site-dependent coupling strength. Okay, so how do we exploit this permutational symmetry? Well, that's just basic quantum mechanics. You've all heard about these angular momentum operators. For the large spins, you can just choose an eigenbasis of Jz, and it has these two quantum numbers, J and M, and J is just, in our size, determined by the system size, right? So, for example, if I think of just three two-level systems, I have, well, 2 to the 3 makes 8 states overall, and they can in principle couple. So in this sequential or recoupling approximation, it turns out that they can only have transitions of single flips or single excitations here. That means that not every state can couple to every other state, so you only have this ladder-like structure. However, the permutational symmetry, I mean, of course you can write down the master equation, get a fancy quantum master equation coupling coherences and populations, but you're doing a lot of work then, and in principle you can of course write down immediately the symmetrized angular momentum eigenbasis, which looks like this. And you see here already in this rate equation, or in this equation, you have only the perfectly symmetrized states, which are highly entangled also. These are the decay eigenstates. And the advantage of doing this in comparison to this is of course that you get a simple rate equation in that basis only. So it's constrained to a subspace of the full evolution. And this is of course only valid if you have this perfect symmetry and if the coupling to your reservoirs doesn't disturb it, right? So what does it look like? You have this Lindblad form, the normal commutator with the system Hamiltonian, and large raising and lowering operators, and to remind you, just they raise and lower this quantum number m by plus minus 1. These gammas here are the spontaneous emission rate of a two-level system, also derived microscopically from this coupling constant, and these n are the bosonic occupation, so the Bose-Einstein distribution evaluated here at the transition frequency of the system. So now you can check, of course, well, the stationary state is just thermal with the same temperature as the bath. And you can also solve that if you just couple to a single bath. You can solve that, solve for the dynamics, and recover these previous results that you get this transient Dickey flash. Even though you might question this applicability in this regime. But now we are asking, I mean, what's the long-term evolution? We are mainly interested in the stationary state. Okay. And the stationary current. So, and here it turns out that because we have the symmetry, we can easily solve for the stationary state, namely simply by defining this average occupation as a simple weighted average of the two bath occupations. So it would be the thermal state which you would have if you would couple to a single hypothetical bath that has some average temperature, which you can simply define that way here, right? And this is because you only have a single transition frequency. If you would have multiple ones, then that wouldn't go through as simple as it is. So you have a simple thermal state, even though you may couple to reservoirs that are completely out of equilibrium, right? I mean, they are on themselves, they are on thermal equilibrium, but they have different temperatures. And now to obtain the full counting statistics, you could either, of course, do the microscopic derivation in the weak coupling limit, or here I present the sheet where you identify the superjump operators responsible for emission and absorption processes in the system. And then you can set up the set of the connected set of n-resolved master equation and Fourier transform it, or you directly do it by inserting these counting fields here, and that gives you your master equation. And if you now sandwich that in the energy eigenbasis of the system, you get a rate equation. And if you are now interested in the stationary current through that, you can use this little trace formula we had, do the math, and get that very simple expression. So product of these gammas, which has to be reasonable, right? I mean, current has to vanish if you cut away one bath. And the difference of these two occupations. And source is the source occupation, and then drain is the drain occupation, times some collectivity parameter. And this collectivity parameter is now the interesting thing to look at. It actually, so for n equal 1, you reproduce previous results. That's one thing. But for large n, it's possible to write this in a single parameter scaling form. So where it basically only depends on the ratio of this average occupation versus the system size. And that enables you to discuss low and high temperature limits. So if the baths are at high temperatures, you get an anomalous scaling of this factor here. That means that your current is not, the stationary current is not now proportional to the number of atoms n, but n squared. So we have somehow transferred this Dickey effect to some stationary regime, which is quite interesting on its own. For example, you can make it explicit if you look at this infinite thermobias regime, right? But it's not only specific to that regime. You can simply put n drain is 2 times, the other way around, and source is 2 times n drain, and then send both to infinity. So if you're worrying about this Markovian validity. Nevertheless, it doesn't break the thermodynamics. So we can still calculate this fluctuation theorem for entropy production. In this case, it's a fluctuation theorem for heat transfer. And it assumes this simple form, which you would also have for a single two-level system. Okay, I said, well, we can do the full counting statistics, of course, while doing some tricks on the Laplace transform. And if you consider just a vanishing drain bath, so vanishing drain occupation, vacuum bath, and now change the source occupation. Of course, when they equal, there's no current, but here you have some linear regime, but, and then you also have a saturating regime. So that's the maximum conductance of your system. And you see, first of all, here, so the solid lines is for n equal 1, then dashed for 2, 4, 8, and you could go on like this. And the different colors denote the different cumulants. So cumulant first is the current, second is noise, and then it's the third and fourth cumulant. First observation is that initially and finally the spacing here is different, and that's simply this different scaling behavior, right? Here it's linear in the system size, and here it's quadratic. Second observation is that in these two regimes, it's Poissonian, meaning that all the cumulants are equal. And, well, you can also understand that using an alternative approach. However, in between, statistics is non-Poissonian, all the cumulants are different. In this intermediate regime, you actually see that in a regime where the current basically looks still linear, in the system size, the higher cumulants already show some collective effects. I mean, why is that the case? There's some mathematical theorem stating that cumulants of independent stochastic processes are additive. So if these processes would be additive, the cumulants would simply scale with n, right? So here it's clearly some signature of some collective effect. Questions so far? How much time have I got?
About 10, 15.
Okay. Okay, of course this result is independent on the basis choice, so you could do this discussion in the localized basis, but then you have to keep the coupling to the coherences, right? Because you have this delta, it's not a delta in the states, but a delta in energies. Now that's also a problem because, well, what what do you do when you have near degeneracy? So if that symmetry I've talked about is slightly broken by whatever additional process, and you do this secular approximation scheme, you get a completely different evolution, incoherent evolution, and which one of the two solutions is correct? So then the secular approximation fails. So actually what you have to do is to think what has changed, what's the new correct pointer basis to which the system is relaxing. And there are different possible scenarios how to resolve that. One idea goes back to Maximilian Schulz and Felix von Oppen. They propose to assume in the subspaces which are near degenerate some singular coupling limit where the interaction Hamiltonian rotates further the basis. And another one is due to us to generate some propagator via coarse graining. So circumventing Born-Markov approximations just coarse grain the dynamics. It's not clear which one of the two approaches. They are different in the long-term limit. So this will always collapse to the secular approximation just via time, and this will give you different stationary states. So you can distinguish between these two ideas. But the main message from this part I would like to tell you is that coherence can significantly alter this transport. And with this, if I have still a bit of time, I would like to discuss the Ising model as the next generalization. So here, instead of non-interacting systems, we do have a spin chain, which is described by this Hamiltonian. So you have some paramagnetic term, some external magnetic field, and this is some ferromagnetic interaction term. And basically the same interaction with the two baths. They are also bosonic. Now, here also the symmetry of the system is respected by these reservoirs, and for a single bath we would also expect thermalization. Why is this interesting? Well, that system has a second order quantum phase transition even in its ground state for G equals J. And we would like to understand how does that affect the transport. So the general technique to treat this kind of system is to apply a certain series of mappings called Jordan-Wigner transformation, Fourier transform, Borel-Liouville transformation. It's a bit technical, but what you see here is that this first transformation, it maps to fermions that are non-interacting, and therefore you need this bunch of operators along the chain to make them anti-commute, right? The Pauli matrices they commute on different sides, but these fermions have to anti-commute. You do that mapping, and you get a very simple form of the Hamiltonian where this dependence on these parameters here, we've mapped this into a phase parameter S, comes into this dispersion relation here. And this quasi-momentum K now is only allowed to assume discrete values for finite chain length. You can do the same for the interaction, and it becomes a bit of a mess, but it's actually not so bad, because if you look at that interaction part now of the Hamiltonian, it maps, well, this is just a dephasing part, right? So it's not so problematic in this energy eigenbasis. But this part here, you see, it always creates pairs of quasi-particles of opposite momenta. So that gives you some opportunity to reduce the accessible Hilbert space. And if you plot that, this is the full spectrum. So the full dotted lines is the full spectrum of the Ising model for n equals 6. And now the subspace we are looking at is only the one where you have only quasi-particle pairs of opposite momenta, so it has half the dimension, right? So the full dimension is 64, and here you have only 8, and you can calculate all of these things analytically. As you increase the system size, you get more and more lines here. What's important is that you only have transitions of single pairs, basically, of quasi-particles here. So you have only these allowed transitions between the black and red curves, and red and blue, and blue and green one, where you have 3 quasi-particle pairs. And all these transitional energies are now different, so it's interesting on its own to study that. When you increase the system size, the energy gap above the ground state vanishes as 1 over n, so that's one signature of this quantum phase transition separating a paramagnetic and ferromagnetic phase. And you have physical interpretations. For example, in the ferromagnetic phase, these quasi-particles count the kinks between domains pointing upwards and downwards. In between, it's hard to get a physical interpretation. So in this subspace we are looking on, we have a very simple rate equation form where it has basically that topology here. So these are the diagonals, and they couple via these irregularly, not completely irregularly, but somehow disordered, no, these are not coherences, but rate terms. So these are jump these are transition rates, which you have on these off-diagonal elements. And you see here you basically recover the known terms which we had from the two-level system, with the exception that you now have in the argument the different corresponding transition energy and some modulation factor, which encodes the quantum critical behavior here. Well, finding the stationary state is surprisingly simple here as well. You can still define that average occupation, and this is a general property of systems where the coupling structure of the Liouvilleans is basically the same for the multiple paths. Whenever you have such a thing, try something like this to get the stationary state and plug it into the equations of motion and validate it. So you can calculate that stationary state analytically, and if you look at that more closely, you see that as long as your two reservoirs are at different temperatures, it's not a thermal one. It cannot be described by a single temperature because you have these different transition frequencies. Yeah? Although, I mean, it's still not very far from a thermal state because you see that with increasing quasi-particle number here, the population decreases. That expression is smaller than 1. Now you can compute with the stationary state, the stationary energy and magnetization by mapping basically these corresponding operators into the quasi-particle picture. And you see that only at 0 temperature you get this signature of criticality, in that the energy density basically, which can be represented by a single integral, is then non-analytic really at this critical point. And you see that for the energy density in the second derivative, that's why it's classified as a second order quantum phase transition, and for the magnetization you already see it in the first derivative. And that only holds in the continuum limit. So for finite chain sizes, everything is finite, but you see precursors, right? Like a dip at least. And furthermore, if you now look at finite temperatures, where you don't only have the ground state dynamics, even in the continuum limit, everything is rendered finite. So if we want to now compute the current, through that we can also do these kinds of manipulations and also arrive at a very simple formula where we basically have the two-level current modulated by these simple factors which encode this quantum critical behavior. First of all, it's antisymmetric when S and D are exchanged, so under source and drain exchange. It's analytic for finite n, but you can now transfer this into an integral when you consider infinite chain sizes and analyze the structure of the integrand to see if there's critical behavior. And here it turns out that for all the different configurations far from equilibrium, you see that the second derivative is non-analytic. So it's somehow opposed to the pure system properties that don't show that, right? There it goes away, the criticality, at finite temperatures. Okay, you see that, so in this plot we also do this for finite chain lengths, and in the current, which is here in the main, you see that basically 40 is quite a large number already to get close to this continuum limit, which is due to the fact that this is a rescaled plot, so we divide the current by n. So here it's not like a super anomalous scaling, you only get this in the second derivative. And this holds even far from equilibrium. So we propose basically to look at the current instead, if you don't manage to measure system observables itself. So what happens now if you look at slightly disordered couplings? Well, in that case, you can't simply neglect these thin dotted lines. Now they become thicker, and the system will spend, at least for slight disorder, part of its time in the other subspaces. And what you will have is a near multistable system where you have transitions between subspaces occurring slowly, and that will produce you in general telegraph noise. If you look at the stationary current, all these separate currents will be averaged and so enter additively. That means that we expect in this case that this sensitivity should persist. If you do it now completely asymmetric, like consider transport through an open chain, that's a different story, of course, and it has been treated though with some phenomenologic assumptions on where basically the Lindblad operators were chosen local already. But that's not a microscopic derivation, and so it's still a question of debate how to phrase that properly already. Okay, I think I have to close, and I would just like to say we just discussed these primitive quantum systems with the hope that, well, you might learn some great deal of interpretation. How might coherences enhance transport, for example, or what should happen if you have some really quantum system and do transport through this, and now transfer this to larger objects. Okay, so let me thank my collaborators. Malte Vogel is a PhD student, and Tobias Brandis is head of the group. And you for your attention. Thank you very much.